Today we are going to finish up talking about single replacement reactions and how to predict the products of a single replacement reaction, as well as combustion reactions and how to predict those products. Previously, when we were learning about single replacement reactions, our only goal was to figure out if they were going to occur. And that was by using the activity series over here on the right side. Okay, we didn't try to figure out what they were going to do, we just were trying to figure out if it happened or not. So, if you recall, right, that the generic formula is A plus BX yielding AX plus B, and our statement was that if element A is above B in the activity series, the reaction occurs, and if B is above A, then no reaction happens. That was how we determined whether this was going to occur or not. So the question becomes, how do we actually predict the second part of this? How do we actually predict the AX plus B part of it? We know it's going to happen, so how do we know what the products are going to be? So when you see single replacement reactions and it's asking you to predict what's going to form, you're going to need two things. You're first of all going to make sure that you've got the activity series handy, okay? And the second thing you're going to want is your ion sheet, okay? Without both of those, you can't really do these effectively. So the first example here, let's take a look at Mg plus FeCl2. Okay, so if we label things as A and B, right, if Mg is my A and iron is my B, magnesium is the A and Fe is the B, magnesium is here, iron is right here, magnesium is above iron, so yes, this reaction will occur. So now it's time to figure out what actually forms. Well, remember, right, this is a replacement reaction. A and B switch places. So on the product side of things, the iron is now in its elemental form. We would see elemental iron forming. The other thing that forms here is determined by the ions and your ion sheet. Okay? I'm going to write this off to the side before writing it onto the actual answer here. Magnesium forms +2 ions. Chlorides form -1 ions. Okay, so together with making that into an ionic compound, we get MgCl2. Now, conveniently, that matches up with this formula, right? A and B switching places. It looks like the Mg just stuck in right where the Fe is, right, and attached to the two chlorides. It's not quite always that simple, which we'll see here in just a second. But this would be the correct answer here, right? You have A plus Bx, and I kind of wrote this in reverse. You have B plus Ax. Okay, X can be multiples of things. It's not just one thing here. So the second example, we have nickel plus lead 2 nitrate. So if we label things A and B, right, if nickel is A and lead is the B element, and then we go look over here on the chart, well, nickel is right here, okay, lead is right here, so this is going to occur. You are going to have these things switch. Okay, so we know what's going to happen. And then as far as what forms, well, the easy one is lead just is now my element on the product side. So we will get elemental lead forming out of that. Okay? And then the other thing that's going to form here, again, we'll do this off to the side. Nickel forms a +2 charge, and nitrate forms a -1 charge. So the formula for nickel nitrate, NiNO3 2, like that. Now, so far, the two examples I've given you are really easy because this number right here, the 2 nitrates, matched up with what the charge was on the nickel. Okay, it's not always going to be like that. So this last example here, we have aluminum plus sodium nitrate. Okay, so let's take a look here to figure out, first of all, if this is going to even happen or not. If aluminum is my A element and sodium is B, okay, aluminum is here, sodium is here. Sodium is above aluminum, so this last reaction is actually no reaction. Okay. Now, it's not always going to be this convenient, nice one-for-one swap, which we'll see here in just a moment. I'm going to go ahead and do the first example for you, and then I'm going to ask you guys to do the final two. So we have sodium plus aluminum chloride. So if we label sodium A and the aluminum B, and we come on over here and look, sodium is above aluminum, so this reaction is going to occur. Right, so that means that the sodium is going to knock the aluminum out of the compound, and aluminum becomes the element over on the product side. Well, the Al is really easy, right? We can predict that. The second thing that we're going to get, though, it's not just NaCl3, right? Sodium forms +1 ions, chloride forms -1 ions. So the other product is sodium chloride like that, NaCl. So you do have to be careful Okay, like I was trying to explain on the last slide there, it's not always just a one-for-one swap. You have to pay attention to the charges. Aluminum had a +3 charge here, okay? Sodium only has a +1 charge, so the product is just NaCl, not NaCl3. Go ahead and try these other two. We'll ask you questions about them, and then we will analyze and see how you did. Okay, so let's go ahead and see how you did here with this. So the second one, iron plus lead 2 nitrate. The iron is above lead, so this is going to happen. The easy product to predict is the lead, okay, the element lead. The compound, now you can make iron +2 or iron +3, and depending on the circumstances of the reaction, you could get either one. So technically, you could write FeNO32 or FeNO33. Either is acceptable here because the charge of the iron was not specified, okay, previously. It didn't say iron's going to form a +2 charge, okay, this would tell you it would have been this one, or iron's going to form a +3 charge, which would have told you it's going to be that one. The last one here, aluminum plus 10 nitrate, all right. Aluminum is above 10 over on the activity series, so it is going to replace it. So the easy prediction here is the 10 gets knocked out to be the element. And then the compound that forms, aluminum forms a +3 charge, nitrates -1, so I need 3 nitrates to do that. Now, one thing we have neglected doing this entire time is balancing. Okay, we haven't asked you to balance it. You know how to balance equations. That's not hard. We're not so concerned with that right now because we expect you to be able to do that. What we're concerned with is your ability to predict what is in fact going to form. Okay. All right, the second reaction we are going to cover today are combustion reactions. Okay, and then the goal is to also predict their products. Now, these are pretty easy to identify and pretty easy to predict what is going to form. So it shouldn't take us too long to get through this. If you recall, all combustion reactions must have O2 as a reactant. In order for something to burn, it has to have oxygen, right? So what actually forms? When you burn something, what do you get? Well, that depends on what it is that you are actually combusting, okay, what you're trying to burn. There's really a couple of options here. There's some other ones on the next slide that I'll show you, but the main types of combustion involve the following. Where you have a metal plus oxygen, burning with oxygen, you get a metal oxide. You use your ion sheet to determine the formula. So an example here, right, your metal being magnesium, oxygen being oxygen. Metal oxide is MgO. Mg forms a +2 charge, oxide's -2, so we get that. Okay, so you might see some examples of those here in just a moment. The other type of combustion is when we burn a hydrocarbon, okay? So that's things made out of carbon and hydrogen, plus oxygen, right, since it's burning. The two products you get are carbon dioxide and water. The example here, this is octane, C8H18, plus oxygen gas, okay, yielding carbon dioxide and water, right? You can see some rather large coefficients there for the balanced equation, but that's how it works out. Okay, so this is actually the reaction that happens when you are driving a car, right? Gasoline's got octane in it. Okay, when you burn octane, you need oxygen, so your engine is burning up oxygen in the presence of, or octane in the presence of oxygen, and you're pumping out, 16 moles of carbon dioxide and 18 moles of water vapor, and it's hot. It's not liquid water, though in the winter you can sometimes see it condensing. So for every 2 moles of this, you get 16 moles of carbon dioxide and 18 moles of water. This first hydrocarbon can actually be any other type of organic molecule. So it's really anything that's made out of carbon or hydrogen, and sometimes you'll see oxygen in those formulas as well, which you'll see an example of here in just a moment. So if you burn something with carbon and hydrogen, the two products are carbon dioxide and water. So we got the metal oxide formation and then carbon dioxide and water as the other option. Okay, so let's just take a look at several examples here. This first one, we have barium plus oxygen, so this is going to be the metal oxide situation. Okay, barium on your ion sheet forms a +2 charge. Of course, oxide is a -2 charge. The product here would be BaO, barium oxide, like that. Okay. The second one, we have a hydrocarbon, carbon and hydrogen plus oxygen. You get two products. You get carbon dioxide and water, both of them in the gas form, okay, water vapor. The next one, C6H6 plus O2, same thing. You got a hydrocarbon plus oxygen. You get CO2 and water. Now, again, we could spend the time here balancing it. We're not so concerned with that. You should be able to do that. That's in your skill set. We're not going to worry about it right here. It's just enough for you to realize, okay, I'm burning a hydrocarbon. I get carbon dioxide and water. Well, what happens instead of a hydrocarbon? Let's say it's just carbon. This example right here, the C plus O2, where might you see this? Well, this would be something like charcoal. Okay, so if you have a gas grill, sorry if my dog's barking in the background there. If you have a charcoal grill, okay, like a Weber charcoal grill, and you're burning charcoal, that is just pure carbon. Okay, there's no hydrogen in it; it's just carbon. Okay, bricks of carbon. Well, in the presence of oxygen, what you get from that is carbon dioxide. That's it. So when you're burning charcoal briquettes, right, you get carbon dioxide. Well, why no water? Well, there's no hydrogen here. We have to have hydrogen in the formula to get water. Okay, so if this had an H, we would expect water forming as well, but there is no H in this particular example. The next one here is the combustion of hydrogen gas. Hydrogen gas is very flammable. The Hindenburg famously, right, caught on fire because it was full of hydrogen gas. Well, hydrogen gas also burns, it combusts. But if you note, there is no carbon here in hydrogen gas. Okay, so the only product we're going to get when you burn hydrogen is water. We don't get carbon dioxide because there's no carbon in this thing's formula. All right. Last example here, this is a chemical called methanol. It's a type of alcohol. It is a type of hydrocarbon, though it also has oxygen in it. This last OH bit here makes it a type of alcohol. It's got carbon and hydrogen in it. When you burn it, you should expect the products of things that have carbon and hydrogen. It's got CO2 and H2O. So those are the products you would expect. So here are some other examples of things to expect, what to look out for. If we asked you to balance it, we could ask you to do that. I'm not going to ask you to do that here in the notes today. I just want you to be able to predict what's going to form based on what's in the reactants. Okay, why don't you guys go ahead and try these last three, and then we'll see how you do here in just a moment. Okay, so the first one there is the combustion of aluminum. So aluminum plus O2, aluminum forms a +3 charge, oxides -2, so the metal oxide here is Al2O3. The second one, C2H6, that's a hydrocarbon plus oxygen. We should get carbon dioxide and water. This final one here, CH3CH2OH plus O2, this is ethanol. This is the formula for the type of alcohol that's in adult beverages. That's the formula there. Plus O2, burning that gives you carbon dioxide and water. It doesn't matter that there's oxygen here. This is still got carbon and hydrogen in it, so this would be the product we would get. Just for reference, if we ever ask you to balance the combustion of an alcohol, this gets really messy. You have oxygen in all four things. It is a real pain in the butt to try to balance this because every time you adjust oxygen, it messes up all four things there. So maybe a good extra credit question or something like that in the future, but these ones are pretty tough to balance correctly. Hopefully you did well on that. If you have any questions, let us know.